Good morning. Very happy to be here in this beautiful room. I hope you hear me well. And if we can begin. So I'm here to tell you a little bit about the beginning of the journey of Proxima Fusion. It's a company based here in Munich. And I want to begin by thanking the Max Planck Society on whose work we're building. We are the first spin-out in 60 years of history of the Max Planck Institute for Plasma Physics. So fusion, if you know anything about fusion, it is that it's always 30 years away. It has been for a long time. There is this cover of Time magazine was somewhat ironically pointing this out. Fusion could give unlimited energy for everyone, forever. But there was this other part. It might actually work this time. This came out a couple of years ago, and it was highlighting the fact that something is changing in the world of fusion. This slide here shows some of the companies that have gotten started, mostly in the United States and the United Kingdom. Each of these has a slightly different concept. Each of this group wants to get fusion going with either strong magnetic fields or strong lasers, give or take. Everyone has a different idea. There have been $5 billion of private investment in the field at this point. Why are we working on this so much? Fusion is the source of energy inside the stars. If you look at any star, including our own sun, what is burning in the center at about 10 to 15 million degrees is fusion. Fusion is the ultimate source of energy of the universe. So if we could get fusion going on Earth, we would bring really the world to a completely new phase where clean energy can be produced in the most energy-dense way that we can imagine. What is exactly fusion? There are many reactions that we can get fusion going with. This one is the one that Proxima Fusion is focused on. It involves heavy forms of hydrogen, so the lightest of the elements. Here you see at the top deuterium and tritium. And if we take these particles and we smash them really hard, they can overcome the nuclear forces and fuse, hence the expression. And the outcome of this reaction is a helium particle, which you probably know, helium is nothing that bad. It's not quite a particle that we are concerned about. There is also this neutron. So that's a really light particle, which comes with an enormous amount of energy. Not everyone has a feeling for these units, MeV, but that is a huge amount of energy. And dealing with these particles is very complicated. On top of helium and neutrons, you get a lot of energy. So what you're really doing is relying on Einstein's formula E equals mc squared. You're transforming some of the mass of the incoming particles into energy. And if you can harvest that energy, then you're in a very different place suddenly. You're in a different place because the amount of energy that goes into a spoonful of fusion fuel is basically equivalent to 11 tons of coal. If only you could get that done, you would be in a new era of how we think about energy. In this representation, this is, in some sense, the history of energy. We started out with muscle power, with animals pushing our carts, and that was really the center of how human civilization developed for a long time. And then we went through the Industrial Revolution. That was the time of chemical energy, when we could take some products that have some higher energy density, burn them, and we all know what happened with that. Then we entered the nuclear age in the modern times, and fission is what many of you are familiar with. Fission involves taking a heavy nucleus and splitting it, and some of the mass will be transformed into energy. This is the process that you are familiar with in nuclear power plants. But the sister process on the other end of the periodic table is fusion. That involves light nuclei that we join. So instead of splitting atoms, we're joining them. And fusion has even higher energy density. So it's even later, both in time, because we're working on it right now. Fission is what we already have with all the good and the bad. Fusion is the next step. So if we can get fusion going, our models tell us that this could be a cheap source of energy. It would be clean. There is no CO2 whatsoever at any point. The amount of waste, radioactive waste that we know is somewhat problematic in fission. It would be an entirely different scale. Safe in the sense that fusion, in the way I'll be describing, does not involve, there is no meltdown possibility. The process cannot run away, so to say. It's very dense. So as I said, it's what burns in the center of the stars. And if we can get this on Earth, it would have a relatively small footprint. It's reliable. And maybe this is the most important thing. As we're looking into a world of clean energy, solar and wind are fantastic, but they're intermittent, and we cannot really fill the grid as we think of it with only solar and wind. We need something that is substituting the fossil fuels in the way they work in the grid as of today. And finally, the fuel that we're talking about is basically heavy hydrogen. And heavy hydrogen, we have plenty of. It's not without complications. There is something difficult about it, as you can expect, but we can power humanity basically forever with fusion. So there are a number of companies that have been trying to do this. I mentioned earlier, these are some of the designs that have been thought about. Some of these, as you see, are built. It looks all like sci-fi, but this is real. This is happening right now. Of the many concepts for fusion, the ones that we at Proxima Fusion see as most advanced, coming closest to actually making energy, are the tokamak and the stellarator. Now, both these concepts rely on strong magnetic fields confining what we call a plasma. A plasma is hot, ionized matter, like the one that you see in the stars. And in both cases, we have strong magnets that produce the strongest magnetic fields that we have on Earth. And you're creating basically a cage. And in these cages, you want to let the plasma follow magnetic field lines. So in some sense, you're creating a bottle. And in that bottle, you need to make sure that this matter that you're heating to 100 million degrees, 10 times and more the center of the sun, you need to make sure that it doesn't touch the material surfaces. There is no material, neither today nor tomorrow, that will support those kind of energies. So in a tokamak, you do this. You see the difference between the left and the right. The left drawing is much more regular. It's toroidally symmetric, we say. So it's symmetric in the long direction. And it's somewhat simple to design, but complicated to operate. It relies on these magnets. You see these blue things, but also in the center, I think this clicker may work, yes. In the center here, you have this core. If you imagine this like an apple, that's the core of the apple. That's a transformer, for those that are familiar with the topic. And this transformer is creating a very large current through the plasma. The plasma here is represented in purple. And this red arrows here represent mega amperes of current. If you have a feeling for how large a mega ampere of current is, it's an enormous amount. On the right-hand side, you see instead something that looks very complicated as a drawing. It's very irregular. You see these coils now are not nicely, easily shaped as on the left. Instead, they're all twisty. This device, in this case, has a 5-fold symmetry, and it doesn't have anything in the center. So the apple core that you see on the left doesn't really exist on the right. So that's a stellarator. The entire confinement cage happens via external coils. And that has some massive implications that also involve increased stability. If you can get this designed, it's more stable. It's easier to operate. The analogy that we like is that a tokamak is a bit like an helicopter. It flies low, so you don't have to know what's going on in the upper atmosphere. You fly low and you are always somewhat at risk. So if you drive an helicopter, you're always sort of driving it and preventing it from crash. The helicopter, the moment you turn off your engine, definitely goes down. You know that for sure. In an airplane, instead, an airplane is a bit more like a stellarator. An airplane, you have to lift it off, and then if it's well designed, it should be stable. If you take your hands off the controls, the thing is supposed to keep afloat. And so that's what we want a power plant to look like, in our opinion. You want something that is like a microwave oven. You turn it on, it just works, and you turn it off when you want it. This is a stellarator. It's not any stellarator. This is called Wendelstein 7X. It's a device within the Max Planck Society. It's in Greifswald, in the north of Germany. And what you're seeing here is the plasma shape, or the cage that we are creating with the magnetic fields. It's the same machine that I showed earlier. Here, this high energy matter is in this 5-fold shape. The way we confine this is with non-planar superconducting coils. On top of that, we have more and more coils, and these coils create enormous forces. And to support these forces, we have these structures, and we have current leads, and because this is superconducting, we need to keep it at cryogenic temperatures. And to do that, you need a cryostat. And once you take this humongous amount of technology and you really close it up, what you see is this thing, which depending on what kind of person you are, you either think, oh my God, that's horrendous, or you think it's fantastic. I'm one of the latter category. I think this is one of the marvels of technology, and it's here in Germany, and we have to build something on this. If you look at this facility, the Wendelstein 7X stellarator in Greifswald within the Max Planck, the facility is much more complex than just the stellarator that you see at the top right. Building this costed Germany 1.5 billion of public investment. And as we enter the fusion race with Proxima Fusion, this is an advantage that we cannot underestimate. There are a number of things that say that now we need to speed up, that now is the time to invest privately into this space. The Proxima Fusion group got started with physical optimization of stellarators. Now we can overcome what have been considered the drawbacks of stellarators historically. But there are a number of things that we didn't develop and that exist now. They come from industry, and we have a clear view of where they fit in. GPUs, machine learning, additive manufacturing of metals. And then this last thing on the list, high-temper superconductors. They're a strange thing. It comes in tapes. The ones that you see down here are from a company based here in Ismaning, near Munich. And these tapes can reach much higher magnetic fields. They don't need to be cooled to near absolute zero. They ease some of the engineering constraints. And we are working on putting these things together and making net energy with a stellarator. So we see ourselves sitting on top of this treasure that we see as W7X. W7X is currently in operation. Last year, there was a record 8 minutes of operation at high performance. And now the question is, what do we do with these results? So Proxima Fusion started recently to work on a power plant conceptual design. We see ourselves getting that done, building a coherent concept for what how a power plant would create energy based on this stellarator concept. We're working on a number of technology demonstrations involving these high power coils with high temper superconductors. And all of our program is aimed at the final product. So instead of working on the intermediate products, step by step, we're working on what we call Proxima Beta. This is a stellarator reactor that we see as, we model to produce a levelized cost of electricity. So the value that an energy company cares about as being about $40 per megawatt hour electric. And if you have a scale, that's a very interesting thing for an energy source that would be reliable, that would complement the renewable energies that we have today. Coming towards the conclusion, so we are starting this journey as the first spin-out company from the Max Planck in 60 years of history. We see W7X as really being a visionary investment that we need to do something about. We're standing on the shoulders of giants, and now is the time to get this moving. And we don't want to really do this alone. We are in partnership with the German industry and European industry that have been working on W7X and other projects. Some of the partners are listed down here. That's the group that got started in April. So we incorporated the company in January. We were financed already in February, and the team moved together from the Max Planck, from MIT, and from Google. We're all here in Munich now. I conclude here. The journey is bringing us to catalyze a change in the way fusion energy is going towards stellarators, which we see as the most promising concept to make fusion energy on Earth. High-temper superconductors and design offer us the opportunities to really lift this off, bringing it from a research field to engineering, from a control problem of dealing with the complexity of the physics to an engineering problem. And I conclude by saying we're an early team. We're looking for help. We're looking for the best people that we can find across a number of fields. If you're interested, if you're excited about this mission, please just write me a message. We're looking for people from the operations side to engineering of very many different ways. Thanks for your attention.
Thank you very much for kicking off the second day here at the Festival of the Future, Francesco. Now we have time for some questions from the audience. What are you interested in? Yeah.
Would you be able to describe a bit the innovation and how long it takes? For example, you have some sort of idea, you run a simulation, what you would change, and then you change it. How does that work?
Yeah, let me refer back, maybe starting from this picture here. So we have the models to simulate the plasma physics. This is not an effort on physics. The Max Planck Institute for Plasma Physics is arguably the leading world institution for the topic. What Proxima's objective is to take this and integrate it into an engineering-focused program. So the question about the magnets, if we use these high-temperature superconductors, how high in magnetic field can we go? We think we can build a coil that can go to 15 Tesla on the superconductor. 15 Tesla produces forces that could lift a few TORFLs. So putting these coils together, not just one, but a few tens, and holding them together is not something it's not a challenge to be underestimated. That's the kind of system integration challenge that we're talking about. And once you go from an experiment to a power plant concept, then the question is, how do you capture the energy? Our experiments today are not made to capture energy because we're doing physics mostly. But if you are interested to talk to energy companies, they will ask you, what is the concept? How do you connect to the turbines? And then questions about how do you capture the neutrons that I talked about at the beginning become very important. And those are engineering questions. They are about development and not so much fundamentals of physics.
Yeah, Daria.
What about the cost of energy then?
Sorry?
The cost of energy.
Yeah, so this cost here that I mentioned, this $40 per megawatt electric, it comes from a system code that we have in-house. This basically takes configuration, so the kind of strip, in this case it's a Mobius strip, the description of what the plasma achieves in terms of performance, and it counts how much each component costs. It takes into consideration the cost of maintenance, the cost of the downtime, how long it would take you to change one part versus another one. It's this code that we are using, it's at academic level of both rigor and conservatism, and that's the number that it comes down to. This is the kind of number that it comes from taking, for example, if you have 50 coils, you count 50 times the same cost. So there is no discount factor. This is, I care to highlight this. This is not a number that today we can promise that we will achieve, but this is possible. This we know and we truly believe.
Maybe for a little bit context, for the consumers, we don't talk megawatt hours. We talk in most cases kilowatt hours, right? And this is factor 1,000
4 cents.
Means 4 cents, which is significantly lower than what we pay today.
It's about photovoltaic cost, but photovoltaic cost as of today, and photovoltaic will become cheaper, one may say. So the market, the techno-economic analysis of how energy markets develop is nothing so simple. But if one looks at the International Energy Agency projections, for example, what is very clear from every analysis is that the sources that we know and love so much, wind and solar, for example, they will not scale above 50% of the grid. They become more expensive once they become the dominant sources. You need something that fundamentally burns. And that burning, today we take from coal, we take from gas, we take from fission, and that's what we're going after.
Yeah, thank you very much.
Mm-hmm. Mm-hmm. Right.
Is that something that keeps you up at night, that storage becomes so cheap that we don't need fusion anymore?
What keeps me up, and maybe I repeat briefly the question. In summary, could the advancements in batteries really put fusion out of the market? What keeps me up at night is the possibility that we don't think about having multiple options. I'm not so worried about fusion not finding its place. What would be worrying is if we say, batteries are amazing, and the more buzzwords you put in the topic, the better you are. And you make a bet, and then you fail that bet, because such is the life of technology development at these scales. Fusion, we're not advocating for everyone dropping what they're doing and listening to Proxima Fusion, saying, we're going to get fusion going, you guys relax. That would be a terrible idea. Like it's a terrible idea to say batteries are enough, because there are a lot of uncertainties in the batteries. It's not so easy to imagine. One thing is to say, what is the cost of solar, of the photovoltaic? One thing is to couple it to the storage. One thing is to talk about the amount of energy that you will need to do carbon capture, to do desalinization. There are some things that you would not want to do, I would bet, with solar plus batteries. If you think, for example, about what is the source of energy that you want to melt metal, you should talk to somebody that works in metallurgy or in glass things, and you find out very soon that they don't use photovoltaic, neither with nor without batteries, not even direct, not even when the sun is shining, because to melt things, you need 800 degrees, and you need something to burn and to transfer heat at 100 degrees. So there are some aspects of the energy market that will not be substituted with batteries. So I'm answering your question in many different ways just to give some ideas.
Yeah.
My bet is that there is a place for different solutions that look completely alike.
I'm really thankful for your question and for the answer you gave, because two topics you just mentioned, which is batteries and which is carbon capture and storage, are actually topics that we will discuss this afternoon at Festival of the Future. Not on this stage, but outside on the art stage. So maybe you can ask the same question there as well. Are you threatened by fusion technology then? So thank you very much. I think we have time for one last quick question and a quick answer. Yes.
This coil that you see here is designed to be a high-temperature superconducting coil reaching 15 Tesla on the magnet. This is what we think we need to get done. We haven't done it. Our models tell us that we can, but it's to be done. And until we demonstrate this thing, we shouldn't. You have to build one before you build 50. So now we're working on the one. If we believe to be able to make that, we believe that we can make that. So it's all about what we're doing now, the system concept, the coherent concept that, from our perspective, other fusion startups are currently missing, and then demonstrating that you have the technology in there. In terms of business, we're looking for the connections to the energy companies, which we see as our final customers. We're not trying to substitute neither RWE nor Siemens. We're trying to do something that none of these organizations have. So we're trying to enter the energy market and sectors by providing a burning core. For us to be able to speak to those companies is part of our business necessities at this stage.
Perfect. Thank you very much. If I were you and had some more questions, I would just try to reach out to Francesco afterwards, either today or via email, via LinkedIn, or any other channel to contact him. Again, a huge round of applause. Many thanks, Francesco Sciortino.
Thank you.